Yes, so welcome to our series of talks. So this is going to be a two-part series, as Andrew mentioned. The first talk will be given by myself, and it will be more of an introduction to the kind of growth models that we want to study. And the second talk will be given by Frankie, and that one he'll be going into more detail on the methodology that's used in order to study the processes and go a little bit more into detail on that. So what I want to start by doing is just by giving an outline of the talk that I'm going to give today. So the first thing I'm going to go through is the real world processes that these conformal random growth models are built to study. Then we'll go on to discuss the lattice-based models that have typically been used in the past to study the models, before going on to the conformal models themselves and describing their benefit over the lattice-based models. I'll introduce the Hastings-Evertov model, and near the end of the talk, I'm going to go into some results. But really, this is just to highlight the properties that we might want to study themselves, rather than going into any kind of real detail on the results, because that will be something that Frankie does more in the second talk. And in his talk, like I mentioned, he'll go more into the methods used that are often used to study these processes. The target audience is obviously early career researchers and postgraduate students. So for that reason, I expect most people won't have seen these models before. So I'm going to try and take it quite slow in this first lecture to give this introduction. But if at any point I am going too slow, feel free to stop me and ask me to speed up. And as Andrew said, if you want to ask questions, hopefully Frankie can highlight any of those to me during the talk if it needs to be answered at that point. Otherwise, I'll try and finish 5 minutes early so that we have time for questions at the end. Okay, so I think we're ready to make a start. And what I want to start by doing is providing some motivation for the real world processes that we want to model using this conformal random growth setup. So what we're interested in is where particles attach to the boundary of a cluster one by one according to some kind of random distribution. And one example of that within the real world is tumor growth. So what you can see on the board here, on the slide here, is research done by Gurley and Anderson, and the paper's highlighted at the bottom here. And what they're looking at is how the levels of oxygen in the surrounding tissue of a tumor will affect what the shape of the cluster looks like in the limit. So obviously this is not, in this case there, it's not dependent on what the tissue is. So there's obviously that caveat in terms of it could be tumor in the lungs or tumor in the liver, for example. They're not taking that into account here, and obviously the modeling in 2 dimensions. But I really think it kind of highlights what we're trying to look at here. From these simulations, what we see is in the case of A here, this corresponds to a low consumption rate. So we're looking after 90 cell generations, and a low consumption rate corresponds to a high amount of oxygen being available to the tumor. And what we see is this growth to a disc-like pattern in this case. The different colors represent the status of the cell, but that's not overly important in the context of our talk. So we can just consider, say, the dark blue region. And you see that we get growth to this disc-like shape. Whereas once we start to increase the consumption rate or reduce the amount of oxygen available, we're starting to see these gaps forming in the growth of the tumor. It still looks somewhat disc-like, but we've got these holes in the growth and certain directions in which the tumor's not growing. And then when we increase the consumption rate by a factor of 5 and significantly decrease the amount of oxygen available, we've now transitioned to this shape that's very much non-disc-like, and it looks a bit like a branching process with diffusion on the boundary. And from a scientific perspective, you can see why someone would be interested in this. If you were trying to remove a tumor from an individual, you can see how this is going to be very closely related to how easy that tumour is to remove is going to depend on what the shape of the cluster is. So in the case of C, you can imagine that this might be slightly more challenging to remove because of its less well-defined edge, whereas in the case of A, this might be slightly easier to remove. But from a purely mathematical perspective, what we're seeing here is this transition from, by changing some variable, we're getting phase transitions from growth to a disk to growth to very much not a disk in this case. And that's something that we'll see highlighted throughout the rest of the talk and is kind of a feature of these processes as a whole. But these are not the tumor growth is not the only example of where these growth processes are exhibited within the real world. Other examples include bacterial growth, biological cell growth, mineral aggregation such as crystal formation, and lightning strikes. So when lightning strikes a surface and forms a pattern in that surface, that's an example of a growth process that would fall into this general category of random growth processes that we want to study. And actually the study, the class as a whole is fairly wide, and there's quite a lot of real world processes that you can study with this, so that's why it becomes fairly useful. So how do we actually go about studying these processes as a whole? Of course, we need to build models. And probably the most natural and intuitive way to build a model on this case, and also probably the easiest way, is to build the models on a lattice. So examples of that include DLA, so diffusion limited aggregation, and the Eden model. Some of you may well have heard of these before. They've been well studied, but if you've not, don't worry, because in the next couple of slides I'm going to go into those, give the definition of those and actually go into some of the results in those in the next couple of slides. But before I go into any kind of detail, what I want to start by doing is just kind of giving an idea of, in general, how are these lattice-based models formed. So they're often built on a square lattice, such as ZD. In this case, obviously, we're in 2 dimensions here, but it can be built up to any dimension. And we usually start with a point, which is usually origin, and we say that belongs to the cluster which we're trying to form. And then at the next stage, we can attach to any one of the boundary points. So in this case, we've got 4 different points we can attach to. I'm not sure if you can see my mouse, but the one above, the one to the left, the one to the right, and one below. So there's 4 possible choices here. And we're going to attach to those according to some probability. And that's going to be the key thing here, is how do we actually choose this probability? How likely am I attached to one point in comparison to another? But say in this case, we might attach to the one above. And now this leaves, we can attach to any of the surrounding points of the whole cluster. So now there's 6 points that we can attach to. And then we might choose the one on the right and then the one to the left, for example. And you can see how this would form. Hopefully you can see here how this would form a growing cluster that might, as we let the number of particles or the number of edges here go to infinity, you can hopefully see how this might start to look like some of the real world processes that we might want to model. But as I said, the key thing here is, well, how do I actually distribute these kind of attaching points? How likely am I attached to, say, the one on the left here as opposed to the one on the right? And that's going to change dependent on what we're trying to model. So let's consider our first example, which we mentioned on the last slide, which is the Eden model. Now, this was introduced in the 60s by Murray Eden. And in this case, what we're trying to model is biological cell growth. So we're trying to model a process where we start with a particular organism, and that cell then divides into 2 daughter cells, which in turn will divide into more daughter cells, and so on. And how we're going to model it is exactly the same way that we set up on the last page. We're going to consider it on the square lattice ZD. And we're going to, how do we attach to the next point? So we start with a connected set Kn, and we're going to attach to one of the points on the boundary of Kn. And the key thing here is what probability do we attach to those points? And what as it turns out, in the case of the Eden model, we're trying to model this cell growth. In this case, the best thing to do is to choose the attaching points equally as likely. So we just attach according to uniform measure in this case. So this on the bottom of the screen here, what you can see is an example of how this might grow out. So the green particle here represents the most recent added particle, whereas the white cells are where we could possibly attach to. And we might attach to the one on the left in this case, and then we're left with 6 possible points that we can attach to, and then the one above. But note, this isn't proportional to how many possible boundary points we could attach to, in the sense that this particle here has 3 points that we could attach to, whereas this particle here only has 2, as the way it's grown out. But due to the fact that we've used uniform measure on the boundary is equally as likely to attach to any point, you might expect this growth, when we look at the shape, which is what we're going to be interested in, like on the very first slide where we're looking at tumor growth, we're going to be interested in the shape in this case. You might expect the growth to be isotropic, because we're equally as likely to attach to any of the boundary points. So you would think in some sense it would be symmetric. But what simulations have shown, so this is a simulations done by Frechet, Stauffer and Stanley in 1985, and they're doing some simulations on the growth of the Eden model. And this is just their simulations with the middle portion removed so that you can see the boundary of the cluster more easily. And what you see in this case is actually the growth is looking anisotropic. So we're looking to this kind of diamond-like shape in this case, which is somewhat surprising. But then in terms of rigorous results, we have the following result, which was proved by Richardson in 1973 and then improved by Keston in 1993. In this case, we're letting Kn be the Eden cluster with n particles. And the result says there's a non-random convex set K, such that once we rescale by the radius, value r of Kn minus at the bottom is the radius of the cluster. And what I mean by that is the maximal distance from the origin that still belongs to the cluster. Once we rescale by that, we can bound above and below by this non-random convex set. Here we're considering the continuum version, so that's just quite similar to what we drew on the last slide. And this complies with the simulations we saw on the last page. But I think what it really highlights, actually, already we can see that it's actually on these lattice-based models, it's actually very challenging to get rigorous results in terms of what shape we converge to. So let's look at another example of that. In this case, we've got DLA. Now, this was introduced a little bit later in the 80s by Witten and Sander. And in this case, rather than modeling cell growth, we're looking at mineral aggregation. So this kind of idea of crystallization is included in that. And the setup is exactly the same. So we're on a lattice and we're considering how the particles grow. What's the probability of the particles attaching to on the boundary here? But instead of attaching uniformly in this case, we're going to attach according to harmonic measure. So I'm sure most people will have seen the definition of harmonic measure before, but what does this mean? It just means that we're starting at a point sufficiently far from the origin, and we're conducting a random walk on the lattice until we attach at one of the particles on the boundary. And then once we hit that particle, the first time we hit one of those particles, that becomes part of the cluster, and then we repeat the process. Okay, so we're in 2 dimensions here. And then again, this is just an example of how this might occur. So the red line here is meant to indicate the random walk. So we start with the red particle, and then we can attach the one below and the one to the side. But rigorous results on DLA have been very difficult to come by. And many good mathematicians have tried to study the problem, and there's been very little success. One of the only real results we have on the area is due to Costa in 1990. And then again, we're looking at, in this case, we're looking at the radius again. So the maximum distance still belonging to the cluster from the origin. And we're trying to find bounds on this radius. Now it's clear that we have one trivial bound, that is the upper bound will be n. If we just had n particles in a line, then clearly we're going to be of distance n from the origin. So we have an upper bound of n here, but we want to try and improve that, and Costa managed to improve that by saying that we've got some constant dependent on the diameter here, the dimension here, such that we find an upper bound of n to the 2 over d plus 1. So that's quite a significant improvement, and it rules out this convergence to a one-dimensional line. But because we don't have a lower bound, this actually doesn't rule out the case that we might converge to a disk, like was the tumor example at the start. Okay. So, as I said, the results on DLA and lattice-based models in general have been very difficult to come by. And part of the reason for that is that when we're studying these lattice-based models, there's very little tools that we can use in order to actually tackle the problem. So that's why this conformal random growth model idea has been introduced. The idea is, rather than modeling on a lattice, we model in the complex plane, and we compose conformal maps in order to form the cluster. Now, the benefit of doing this is that rather than trying to study the cluster as a whole on the lattice, we can study the individual maps, and we can use complex analysis techniques on those maps. And that will then tell us about the structure of the cluster as a whole, rather than having to study it all in one go. But of course, these off-lattice models were built for a reason. We wanted to study a particular process, so we don't just want to discard the off-lattice models completely. The lattice-based models completely. Instead, what we want to do is to construct off-lattice versions of those maps, so that we can still find results on, for example, in the case of the Eden model, on cell growth, and in DLA in terms of mineral aggregation. We still want to find those results, so we have to construct an off-lattice version using this conformal random growth method of the original lattice-based model. Okay, and that's something that I'm going to go on to in detail in the later part of the talk. So before I actually construct the conformal random growth model, what I need to do is to introduce a notion of size to do that. And what the notion of size we use in this case is logarithmic capacity. So what we're going to be considering is maps that take the disk to itself with some particle attached on the boundary. So we need to give those maps some notion of size, and what we choose is to take logarithmic capacity, which is defined as the limit as z tends to infinity of the log of the derivative of the map. So what that means is, if we have a map of the form f of z equals e to the cz plus some lower order terms, and that's exactly the kind of map that we're going to be considering, then this map attaches a particle of capacity c onto the boundary of the unit disk. Okay. And the next slide, I'll go on to the kind of relation between this value c and the actual size in the sense of area of the particle. But this is going to be our notion of size throughout the rest of the talk. So if it's easier just to think of it that way, you can, whenever we mention capacity, you can just think of size for the remainder of the talk. So how do we actually construct these models? Well, it's done in two parts. The first thing we need to do is define how we attach a single particle onto the boundary of a disk. And then we take several of these maps and we compose them together in order to form the cluster. And that's the second step that we need to consider. So the first step is, how do we actually attach this single particle? Well, the first thing we actually need to do is to pick a particle shape. And that's something that will be discussed later in the talk. But for now, just note that we have to fix the particle shape first before we can do any of this. But once we have this particle shape, there's a one-to-one correspondence between the capacities and the maps themselves. So for each capacity C, so each value C bigger than 0, we can find a map, a conformal map, which takes the exterior of the unit disk to itself minus a particle which has been attached on the boundary at z equals 1 of capacity C. But of course, we don't just want to attach at z equals 1 over and over again, because then we're just going to get a line of particles attached. So we need to rotate those maps. So we define the nth particle map as the rotated map where we're attaching at an angle theta n. And we also want to change the size of the particle we're attaching at each point. So we attach a particle of capacity Cn, which we allow to change with n. And then this next thing is just exactly what I was discussing on the last slide. What is the relation between this capacity and area? So if we have maps of this form, and if the attached particle in this case is a slit, so that's one of the examples of the particles that we could attach, and it has length or diameter dn, then e to the cn is roughly 1 plus dn squared over 4, 1 plus dn. So what that means is that if dn is small, then cn is going to be roughly dn squared. And that's the relation that we're going to use throughout the rest of the talk. So you can see from that how the capacity is very closely related to the area of the attached particle itself. So what does this look like? Well, we're just taking a disk, and we're, via the map Fn, we're attaching some particle onto the boundary of the disk at an angle theta n of size or capacity Cn in this case. Okay, so that's the first step, and that gives us a sequence of maps which we can then use. So how do we actually then form the cluster? Well, it's done iteratively. We start with some compact set, which we call Kn. So in this case, we've got n particles on the boundary. And how do we form the n plus 1 compact set, or the cluster? Well, we know we can find a unique conformal map which takes the exterior of the unit disk into the exterior of this cluster. So how do we form the next map, the phi n plus 1 map? Well, we just pre-compose with the n plus 1 particle map, which is going to attach a particle onto the boundary.
Sorry, Judge. We've got a question.
Oh, sorry.
Sabrina wants to know exactly what you mean by a slit. Perhaps you could give the set explicitly.
Okay, so it's just an interval between, so hopefully I'll just skip a few slides and we'll come back. So it's going to look something like this. So it's a slit where it's attached onto the boundary, and it's just going to be an interval from a point 1 on the disk to some length, which in this case we're calling dn. Does that answer the question?
I hope that helps, Sabrina. Yeah.
Okay. Yeah, so how do we form this n plus 1 map? We're just going to attach, we're just going to pre-compose with the n plus 1 particle map, and that in turn is going to attach a particle onto the boundary of the disk, which will then get mapped into the cluster itself. And that's going to give us a growing sequence of compact sets, Kn. So what does this look like? Well, in this case, we've got n equals 4, and we can take, we can find the map phi n, which takes the disk into this cluster. So how do we attach the next point? We just pre-compose the n plus 1 map, which attaches a particle onto the boundary of this disk. And that in turn, via the map phi-n, will get mapped into the cluster. And we call this map phi-n plus 1. Now, the key thing to note here, and a key feature of these models, is that we choose the attaching angles and the capacities or size of the particles via the map Fn. We choose how they're distributed. But once they're mapped by phi-n, they're going to be distorted. So the attaching angle that I pick or choose how it's distributed in the top left here is not going to be at the point where I attach on the cluster itself. So if we want to attach particles in a certain way on the cluster and of a certain size, then we're going to have to be clever about how we actually choose the attaching angles via the map, the F maps, so that when it's lifted by the map phi-n, we're going to get what we want. So that is the key step actually in defining these models to be something that we actually want to study, is how do we choose the attaching angles and the capacities in the way that we, in order to get something that we actually want to study. So that's something that I'm going to highlight in the next construction, which is how do we actually construct an off-lattice version of one of these models? So we have the lattice-based models, and like I say, we still want to study those, but we need to study them using this conformal random growth setup. So in order to do that, we need to consider an off-lattice version of that. And what I'm going to do here is highlight how we actually construct the off-lattice version of DLA. So let's just have a recap. What was DLA? What were we studying? Well, this is on a lattice, and how we're attaching to the boundary points is we're taking a random walk on the lattice, and we're going to run until we hit one of the boundary points. And then we're going to attach that boundary point to the cluster. But now, rather than being on a lattice, we're in the complex plane, and we're going to use conformal maps. So in order to make this work, instead of taking a random walk, we're just on the lattice, we're just going to take Brownian motion, and we're going to run that until that hits the boundary of the cluster, and we're going to attach at that point. So how do we actually pick the attaching angles so that we get harmonic measure, which is exactly this definition here for those who haven't, again, for those who haven't seen it before, if we've got, it's on a set A, we're starting at a point X, then the harmonic measure of a subset or a Borel set of that, that set A is just the probability that the first time a Brownian motion hits is in that set B. So how do we actually choose the angles so that we get harmonic measure on the boundary of the cluster? Well, what that means is we need to choose the attaching angles so that phi-n minus 1 of e to the I theta n shares the same distribution as the hitting distribution of a Brownian motion on the boundary of a cluster. So how do we actually rearrange that so that we can know how we have to actually distribute the theta n? Well, if we, in some sense, just take the inverse of both sides, we end up with, we need the distribution of the e to the I theta n to be the hitting distribution of the inverse of a Brownian motion, but now rather on the cluster, because we know the inverse of the map takes us back to the disk, we're looking at the inverse of a Brownian motion on the unit disk. But Brownian motion is conformally invariant. So that means that when we take the inverse of a Brownian motion, we're just left with a Brownian motion. So now we're looking at what is the probability that a Brownian motion hits a portion of the disk. But the disk is symmetric, and we know Brownian motion has symmetry properties. So that means we're equally as likely to hit any portion of the disk. So the attaching angles we choose are theta n needs to be distributed uniformly on 0, 2 pi. So that's an example. This is an example of how do we pick the attaching angles so that we get harmonic measure on the cluster. We don't necessarily have to pick it in the way you might imagine on the disk itself. We have to pick it in a way that gives us this harmonic measure on the boundary. So in this case, we need to pick the angles to be uniform. So that was quite simple. But what about the capacities? This is the other key feature. We need to pick the capacities in a correct way. But the capacity is a little bit more challenging than picking the attaching angles in this case. So for the capacities, rather than considering the capacities themselves, I'm going to consider the diameter here. Now, we've shown the relation of the diameter to the capacity, but this just makes it a little bit more easy to go through the computation. And we're going to we assume we're going to attach a slit in this case, like we just described. Again, because computationally that makes it a little bit more simple. But this can all be repeated for any of the particles which we will discuss later, which are allowed to be attached. So how do we pick the capacities? Well, for each attaching angle, we know we can find an interval that specific interval mapped via the map Fn gets mapped into the particle itself. So we want to see what the length of the attached particle via the map phi, what the length of that map is. That particle is. We know what the length of the map is going to be via the map Fn. It's going to be exactly this length dn. But we want to know what the size is once it gets mapped into the cluster, because that's going to be distorted by the map phi. Well, this is just an arc length calculation, so you can see that at the bottom of the screen here. It's very easy to do. But what you want to note from this is that if you consider this last term in absolute values here, if we take the integral of that and we kind of forget this first term somehow, and we take the integral of that last term, then that's exactly the length of the particle via the map F. Now, we know what that is. We've chosen that to be the diameter dn. So if in some way we can remove this first term, then we can just set that equal to dn. So what can we do with this first term? Well, the first term, again, we know exactly how this map Fn behaves. And this is exactly the benefit of using these conformal maps. Rather than trying to study the cluster as a whole, we're breaking it down so we can study in individual maps. We know how Fn behaves, and F maps this interval, because this is just on the interval that we're considering, we're between 0 and mu n in this case. On this interval, this gets mapped to the particle. So we can replace this with just some value on the particle, so that when you actually look at the length of the attached particle itself, we can say that's approximately given by dn, so via the last term, times this first term here, where xn belongs to 1 plus dn, somewhere on the interval 1 to 1 plus dn. Now, we can then choose what the size of these attached particles is. And in the case of many of the real-world examples, including DLA, we're going to want, as you can imagine, all of the particles that are being attached to be of roughly the same size. We don't want different sizes, because if you can imagine in cell growth, for example, they're all the same size, and DLA is exactly the same. You want particles being attached of the same size. So we set this equal to some fixed value, which in this case we call D. But we want to rearrange for dn because that's the thing that we can actually choose. We can't choose how phi behaves here. So we choose dn, we just rearrange for dn to be this value where it's d times divided by the derivative of this map, the absolute value of the derivative of this map. So that's how we pick the diameter. And the capacity, we remember from where we discussed earlier, is just roughly given by dn squared. So in this case, the capacity that we choose is given by some value c divided by the derivative of the m-1 phi map to the power of 2. Okay, so that's how we construct the off-lattice version of DLA. It's just done in two parts. We need to pick the attaching angles and we need to pick the capacities. And that's how we pick the attaching angles is to pick uniformly, and the capacity is given by this value at the bottom here. But this is just one model, and we don't want to, we don't want to have to change our approach every time we change the model. And in fact, we'd like one model for all of these kind of DLA and Eden that we can used to transform between each of the individual models. So we don't have to keep getting results on every individual model. We can use, when we're using the same methodology, in fact, we can just create a family of models that we can use and study in one go. And that was exactly what was introduced with the Hastings-Levertov model in 1998. In this case, the idea is to introduce a one-parameter family of models, so that by varying this parameter, we can vary between the different off-lattice models that we've built, and then study the models as a whole rather than study the individual models. And it's using exactly the same setup as we had before, using the conformal mappings method. But now, rather than considering individual models, we're going to be considering a group of models. And again, what we're going to be interested in is what the shape of these clusters is in the limit. Exactly the same as what we had at the start, where we're looking at the shape of the tumor. All of these real world examples, we want to be looking at what shape of the limit is. So how do we actually form the Hastings-Levertov model? Well, again, it's exactly the same setup. We just need to pick the attaching angles and the capacities in an appropriate way. So for the attaching angles, we want the local growth rate to be determined by harmonic measure again. So exactly the same as the DLA setup, we pick the attaching angles to be uniform. So that's nice and easy. With the capacities, we choose the capacities to be given by this value here. And as you can see, this looks very similar to what we had with DLA, except now rather than having -2 in the exponent, we've got this parameter alpha. And the parameter alpha is exactly what's going to allow us to vary between the models, because we're just going to vary the size of the attached particle at each point. So alpha equals 2 obviously gives DLA. And when alpha is large, that's going to make the particle size small. And when alpha is big, the opposite. When alpha is small, the particles are going to be large. Okay. So one of the last things I want to go through, we've kind of already come onto this a little bit, and it's something that's been mentioned in passing throughout the talk, before I get onto the properties, is what shapes are allowed in order to actually study these models. So the particle shape is actually a very key point, and clearly, depending on what we're modeling, we're going to want to change the shape. So for example, if you're considering a lightning strike, then that's going to be the particle shape we're attaching is going to be something different to what we would choose in, say, cell growth. So Hastings and Levertov introduce in their original paper 2 types of map, which they call the strike and bump mapping. The strike mapping attaches the slit onto the boundary, which we've discussed already, and the bump map attaches this kind of semicircle but non-empty interior on the boundary of the disk. And other examples of what's allowed in this case, you have which is like a blob map here, where the particles attach all the way around the disk, but it's concentrated more at one point. You've got the slip and the bump map, which you've already described, and this is in this case, you can add a tangent to the disk tangent to the disk itself. So these are all examples of particles which you can attach. But obviously, again, just like we're discussing with the Hastings-Levertov model as a whole, we don't want to keep changing results every time we have to change something. We often don't want to change results based on the particles that we're going to attach. So in general, we often study a generalized particle, which allows us just to recover all of these particles. So if you improve the results in the most general setting, and then you can recover each individual type of particle later on. And so I'm not going to give that mapping explicitly here, because it can change depending on the result. But throughout the rest of the results, you can just imagine that most of them are given with this kind of generalized particle mapping. And then you can recover all of the classical results. And the final thing I want to discuss before I go on to actually the properties of the model as a whole is how we approach the problem when alpha is bigger than 0. So when alpha is bigger than 0, you can consider the capacities here. When alpha equals 0, you're just left with this fixed value c. And for that reason, most of the results have come in the case where alpha is 0. But when alpha is bigger than 0, you've got this dependence on the derivative of the previous map. And that makes these models very, very difficult to study. So in order to study them when alpha is bigger than 0, we often need to introduce some regularization on the model as a whole in order to actually study in the case where alpha equals bigger than 0. So what we do is we introduce a regularization parameter, sigma, and this sigma just pushes us slightly away from the disk itself and regularizes the model so that it becomes easier to study. Now, for example, one example of that is if we choose sigma equals infinity, then the capacities can be well approximated in this case by this deterministic value. So the reason this comes out is that phi n, close to infinity, phi n, the derivative of phi n looks like 1 plus alpha cn to the 1 over alpha. So when you substitute this value in, you're left with this deterministic value. Now that makes the problem as a whole much easier to study because you've no longer got this difficult derivative to account for. You've now got a deterministic value. So that makes it much easier. So throughout the rest of the results, which I'm going to introduce in a minute, if you see a sigma, that's a regularization parameter. If you see a Cn star, it's when we're considering sigma equals infinity. Okay, so I've got about 10 minutes left, I think. So what I'm going to go through it now is just some of the interesting properties that we might want to study on these models. So the first one I want to discuss is the one that we've discussed quite thoroughly already, is that we want to look at what shape these clusters grow to in the limit. So just like at the start when we're considering what the shape of the tumor was, we want to do something exactly the same, but we need some notion of limit in this case if we want to do it rigorously. And there's two main ways to do that with these models. The first one is called a small particle limit. And in that case, as we send the number of particles to infinity, we send the size, or the value c, in this case, to 0. And that's going to give the scaling limit. And this is what's probably been most studied and was introduced by Amanda Turner and her collaborators and James Norris in 2012. And much work has been done on that since then. The other option is to consider the limit under what we call capacity rescaling. So in that case, you're rescaling by the total capacity at time n. So rather than sending the size of the particle to 0, we're keeping that fixed, and we're just rescaling by its total size, so that we're always contained inside the unit disk, so that rather than having small particles attached to the boundary of the disk, we're actually contained inside the disk. And then we let the number of particles go to infinity and evaluate that. So in terms of results on these two areas, these two limits, in the case of alpha equals 0 in the small particle limit, it's been shown that we get convergence to a disk. So that might be what you expect in this case. We're attaching particles of the same size and we're sending those to 0 and we're attaching uniformly. You might expect to get this growth to a disk, and you can see from this simulation by Amanda that actually it's very clear that we get a disk in this case. So you would probably expect that actually in under capacity rescaling, you would get the same limit here. But actually what we've managed to show in a recent paper is that under this capacity rescaling method, we do not get convergence to a disk in the case of alpha equals 0. And actually you can go even further than that and say that not only do you not get a disk, if the the size, if the particles are of a fixed capacity and the maps themselves are of the form that we gave at the start, then there's actually no possible sequence of angles that you can pick. So you can pick a sequence of angles, you can pick whichever angle you want to attach to at each point, and you will still not be able to get convergence to a disk. Now that's somewhat surprising because you would expect both scaling limits to give the same result in this case. You're still attaching uniformly, you're still attaching particles of a fixed size. But I think the difference here, what happens here is that rather than setting the particle size to 0, we're keeping it fixed. So all you see in the capacity rescaling limit is the very last particle. And in the case of alpha equals 0, that corresponds to the particle size being large. So you end up just seeing this large last particle, which is clearly not going to be a disk in this case. So I think this just highlights, by taking different scaling limits, the convergence results that you get can change quite dramatically. So once we've got this convergence result, we know what we converge to, what shape we converge to in the limit. What would we want to look at next? Well, the next thing we want to look at is the fluctuations. So we want to look at how far away we actually are from that object we're converging to. So we found this upper bound on the difference between the object we're converging to and the cluster itself. Now what we want to do is explicitly calculate what that difference is and not just find an upper bound. So it's very similar to the strong law of large numbers and the central limit theorem. So the strong law of large numbers tells us what we converge to, and then the central limit theorem tells us how far away we are from that object. We want to do exactly the same thing here. So we know, we'll know the object we converge to. In this case, we've named it g of z. We want to analyze what the limit as n tends to infinity of this difference is. Now, just like the central limit theorem, we'll often have to rescale that. And these fluctuations are going to be of a certain order, because if we don't, this is either going to blow up or converge to 0. So let's look at an example result on that area. This is a result that we found recently. We've just shown that in the case of alpha equals 0, we don't get a disk, but actually between 0 and 2, we do get a disk under this capacity rescaling limit. So now we know what we converge to. We converge to a disk. So we want to look at how far away we are from that object. And that's exactly what we're calculating here on this first line. We're rescaling the cluster by its total capacity. Note that we've got these CI stars here, so it's the regularized capacity. And we look at the difference between that and the disk. And we show the fluctuations are of order root n, and we can explicitly characterize that difference, what we converge to, and we get this Gaussian field with mean 0 and variance dependent on alpha. Okay, so this is the kind of result that that you often target. Once you know what you converge to, you then want to see how far away you are from. The next natural step is to see how far you are away from that object. The final thing I want to discuss, and I think I've got 5 minutes to do that, is what do we do if the angles we choose are not distributed uniformly? So this can happen in 2 ways. Another model actually that's been introduced is called the ALE model. And that studies where we are allowed to vary the particle, as well as varying the size of the particle, we can also vary the attaching angle. And I'm not going to go into any detail on that now, but that's another model to look up if you're interested in that. But what if we don't choose the angles to be uniformly distributed? Instead, we choose them to be distributed with some law, which we call nu here. So these are 2 simulations that are examples of where that might happen. So on the one on the left, we've concentrated the measure at 3 different points, and on the one on the right, on a particular portion of the disk. How could we actually say what we converge to in this case? We're not going to be able to do it in the same way that we did with a disk, where we just compare the difference almost point-wise, because how do you actually even define this object? So in order to study these processes, we're going to have to do it in a slightly different way. We're not going to be able to find the scaling limit in the same way we did before. So what we study in this case is the harmonic measure flow. Now, what do I mean by that? Well, consider 2 points on the boundary of the image of the disk. We've attached this particle here. Now, what's the harmonic measure between these 2 points? Well, we know as we described earlier, that the harmonic measure is just going to be the difference between their inverses, because we've got this conformal map F. Now, because we've attached this particle in between, when we consider the inverse, this particle is going to be unzipped in a way in between the two particles itself. So that's going to push these particles apart. And the harmonic measure, which is just the angle between the two in this case, because we're on a disk and Brownian motion is symmetric, is going to increase. So the harmonic measure between these 2 points, if a particle has been attached between them, is going to increase. So that's going to tell us everything we need to know about the evolution of the cluster itself, because, I mean, this has been done for the maps F, but you can do this for the cluster as a whole. So you can see how the harmonic measure evolves at each point is going to tell you how big, and if a particle, where the particle has been attached, dependent on what the size of the harmonic measure increase or decrease is. So this is the way we would approach the problem in the case where the attaching angles are not chosen uniformly. And then just an example result of that. In this case, we're looking, there's a phase transition at alpha equals 0, so we can't actually consider the value at alpha equals 0, so we have to let alpha converge to 0. We've got this regularization parameter, but we're looking as c tends to 0, so we're in this kind of small particle limit again. What does the harmonic measure flow converge to? And it's dependent on the value of this alpha c to the minus a half. But if that converges to 0, we get the Brownian web. If we have it tending to infinity, we get the identity flow. And if it converges to some number in between, then we also get the Brownian web, but it's a time change. Okay, so that's the final example of a result. And Frankie will go into more detail on some of these results later on, not necessarily all of them. But that, I think what we want to do there is just highlight the type of interesting properties that you might want to study when you're looking at these models as a whole. So I think I'm coming up to the end of my time now. I just want to summarize what we've done. We've looked at the real world processes, and we've constructed conformal maps, conformal models in order to study these processes. And then we've looked at some of the interesting results. Now, in the next talk, Frankie will go into more detail on how these results are often found. So I'll leave that to him to talk about. And then here's just some references on that I've used throughout the paper. The one that I would actually probably highlight, I've got some more on this page, is this second one down, which is Amanda's done an article for the LMS, and it's looking at exactly this idea of how you construct the off-lattice versions of both DLA and Eden. And I would go and look at that, for example, on the Eden model is a bit more complicated than DLA. So I think that's worth looking at if you found this talk interesting and you're interested in the models as a whole. I think that would be a good place to start. So I think I'll probably leave it there and open for questions. Thank you very much for listening.
Thanks, George. So has anyone got any questions? Well, I have one for you if everyone's trying to think of something. Yeah, Debrina, you can ask first.
Hi, can you hear me?
Yes, I can hear you. Thank you.
Hi, George. So I was wondering whether, so you know, this Keston's paper of the upper bound, so we don't really have any lower bound. So somehow you go from this lattice into the continuum space, and you seem to have very nice conformal maps and smoothing things to work things out. But, you know, do you have any idea as to how Will that somehow anyways help us with the lattice space?
Well, the models in general, the conformal models have helped in the case. So for various values of alpha, we've got lots of results, as we've highlighted, when alpha is not equal to 2.
2, yeah.
We don't have that many results in the case of alpha equals 2. DLA is a notoriously very difficult problem to study, and this is really one of the only results we have on this area at the minute. It's often exhibited that phase transitions, even using this conformal setup, happen at alpha equals 2, and often the case is we know this happens between alpha equals 0 and alpha equals 2. We still don't know what alpha equals 2 happens there, and like I say, you often have to use this regularization anyway when you're considering alpha bigger than 0. So the more regularization you use, the less value, I guess, that result has, because you're no longer considering the model itself, you're considering a regularized version of that model. So in terms of to answer your question, I hope at some point that this will help with solving DLA, and if it does, then that would be great. But at the minute, there has been little progress towards that, I would say.
So have you had time to look at this recent? It's maybe not recent, maybe a year or a year and a half. So Lionel and I think Vittoria was also one of the authors. I saw Vittoria as one of that paper. I think Lionel, Vittoria, and some other people wrote something. I didn't get time to read the paper, so I wrote something about DLA on cylinders. Have you had a time to look at that? Maybe, I don't know.
I've not looked at that myself yet, but that does sound quite interesting actually. So I'll have a look at that.
A very, very long paper, I think, around 40 pages. So.
Oh, right, okay. Yeah, so I mean, that does sound very interesting. I've not looked at it myself, but I would be very interested to do so.
So, thank you. Sorry, I think Amanda is right. I think it was on IDLA. Yeah, she's
okay.
right. It was on internal diffusion. Yeah, I made
okay.
Yeah.
Yeah, so I had a question for you as well, George. I can't remember if I asked you this before, but you introduced this parameter sigma, and in a lot of other settings, sigma is kind of just a technical device.
Yeah.
Where is it? Yeah, which we're using to avoid having to evaluate this map on the boundary, because like if you're using a slip particle, it has poles, it has zeros, horrible things happen.
Yeah.
Is there I guess a kind of physical or mathematical interpretation, justification for using sigma equals infinity?
Not. I mean, the reason sigma equals infinity is used because it provides this nice deterministic value, I think. I mean, it's probably the worst in terms of using the most regularization. You've completely removed all of these correlations provided by the PiNE map. But I think it's the reason it's used is that it provides the first step towards tackling the problem when you don't have this regularization. I mean, it's probably the worst regularization you could use, but the reason it is used is because it gives this value. I don't think there's any kind of real reason why you would pick it otherwise. I don't know if that answers your question.
I mean, it lets us solve the problem.
Yeah, exactly. That's the reason.
As any.